Okay, so now we will be solving Laplace's equation in two dimensions, which is given by partial squared u over partial x squared plus partial squared u over partial y squared, which is equal to 0. And a physical interpretation of what Laplace's equation is that we have the steady state temperature distribution of a metal plate. So at the edges over here, these are the boundary conditions, right? We hold the edges over here at 0 degrees, and then at this edge over here, we fix it to some temperature distribution f of y. It could be like a constant, like uniform, but it's up to you to decide. So we'll solve this problem using separation of variables. So x of y is equal to x of x times y of y. And if we apply this, we should get y of y times partial squared x of x over partial x squared plus x of x times partial squared y's of y over partial y squared, which is equal to 0. And if I divide both sides by x of x and y's of y, and I'm going to set it equal to positive lambda squared, we should get 1 over x of x times partial squared x of x over partial x squared is equal to negative 1 over y's of y times partial squared y's of y over partial y squared is equal to positive lambda squared. And if we do this, we get the two ODEs through separation of variables. X double prime of x plus, that's actually going to be negative, minus lambda squared x of x is equal to 0, and y double prime of y plus lambda squared y's of y is equal to 0. And these are the two ODEs from separation of variables. Okay, now we will be solving for the y part and the x part of the Laplace's equation. So we know that the ODE is going to be this one, and we actually know its solution. I'll just write it down. It's just going to be y sub y is equal to a cosine of lambda of y plus b sine lambda of y. And the boundary conditions we will be applying are Dirichlet boundary conditions. So if you haven't seen my other video, you should check it out. So the solution to this equation with boundary conditions would just be y of y is equal to sine lambda sub n of y, where lambda sub n is just equal to n pi over L, where n is just a natural number. Yep. So this is the solution for the y part over here, and for the x part, we actually get a new interesting ODE, this one over here. Its solution is actually just going to be, I'll write it out, x of x is equal to a e raised to the lambda x plus d e to the negative lambda x. And if I apply Dirichlet boundary conditions and I use a hyperbolic identity, you could see that this will actually turn out to be x of x is equal to 2a sub n sinh of n pi x over h. You can go confirm this result, but this is the solution to the x part of the equation if we apply Dirichlet boundary conditions. So finally, we get u x of y is equal to the sum from n equals 1 to infinity of a sub n sinh of n pi x over h times sine n pi y over L. Don't have enough space over here. And this is actually the general solution to the problem, and the only thing we need to do now is apply the last boundary condition, which is this one over here. And you could work out the Fourier math, but you could use orthogonality and all that Fourier math to show that a sub n is equal to 2 over h sine of n pi L over h, the integral from 0 to h of f of y sine of n pi y over h times dy. This is the full solution to Laplace's equation. I hope this was helpful.